Hello, everyone. My name is Borhan Ahmadi from University of Gdańsk. I'm a postdoc in Pavel Rodetsky's group. I want to talk about optimal quantum control of charging quantum batteries. Here's my outline. First, I introduce the optimization method. Then I generalize it to, first I introduce the optimization method for driven non-dissipative systems. Then I generalize it to driven dissipative systems. Then I apply it to charging of quantum batteries, first to the qubit model, and then oscillator-oscillator model, and then finally the references. So assume that we have a quantum system with Hamiltonian H, which is equal to A0 plus V minus mu epsilon T. Epsilon is the laser field which is driving this system, this quantum system, and V is the external potential. The goal is to send a system initially in a quantum state psi at time 0 to a desired final state at time tau using a control external field. Okay, in order to do this, we construct the following functional J. The first term on the right-hand side is the fidelity between the desired state, the target state, and the final state of the system. And the second term is the running cost on the control field. And the third term is the constraint, which is the Schrödinger equation. And since it's the wave vector is complex, so we have two constraints, and then summing them up, it gives rise to two real of this Schrödinger equation. And psi f here is the bra psi f is the Lagrange multiplier. Okay, and since okay, we're going to maximize this J because we're going to optimize the evolution to get the final state. So we put the variation of J equal to 0, and since we have three variables, psi I, psi f, and the field, then we have three requirements. Okay, and applying these three requirements will lead to two equations of motion. One is for, in equation 4, is for the forward forward evolution with this initial state, with this boundary condition, which is given by the initial state of the system, and the backward equation with this boundary condition, which is given by the target state. And with this, and the field is obtained in this form. Any field, okay, any epsilon which satisfies the above three coupled equations will give an optimal solution for this control problem. These equations are obtained for a closed dynamics in which there is no dissipations. Then I will generalize these to dissipative ones. So in order to solve these, as you see, in order to solve these equations of motions, we have to epsilon depends on both the forward and backward equation. And we have to solve the first one and then put it in the second one, and then it repeat this process. So it will be solved iteratively. First, there were some approaches like by introducing a guess field, and then they solved this equation 4, then put it in 5, and then they repeat this process. And most of the time it wasn't convergent. But then different methods were introduced, like gradient type iteration, which were convergent. And then later, Tanner and others used Krotov method, which was 4 or 5 times faster in convergence. And in our, we also use Krotov iteration method, which is faster. Okay, here is the general scheme of our work. We are going to send energy from a quantum charger to a battery, and we're going to optimize this energy transfer. So in order to do this, we apply a pulse to the charger and we optimize the shape of the pulse such that maximum energy is transferred to the battery. And also we want the energy to be transferred in such a way that maximum work is extract from the battery. In the following, I will explain how to do this maximum extraction of work. Okay, and we assume also that the charger is dissipating energy into the environment, but the battery is somehow isolated from the environment. So since we have dissipation of energy into the environment, the evolution of our total system will be dissipative, and we assume that it is described by the GKLS master equation given in equation 7. Here H is the Hamiltonian of the whole system, rho AB is the density matrix of the charger and the battery, A is the charger, B is the battery, and dt is the dissipator, which is given in equation 8 with D defined in this form. B is the sum operator and gamma is the dissipation rate. Nt is the average number of photons in mode omega 0 at time with temperature T of the bath. Since here our dynamics is dissipative, then the constraint will be so we can start the same functional but with different fidelity, definition of fidelity, and with different constraint. Here, since the dynamics is dissipative, then the state of the final state of the system could be mixed. So we define the fidelity in this form. Okay, rho TGT is the target of the system, the target state that we want, and rho I tau is the final state of the system. GA is the running cost on the field. I will explain in the next slide. And the constraint will be the Liouvillean master equation. And lambda is the Lagrange multiplier. So the GA is the divergence of the pulse at iteration I and the previous iteration. Okay, and lambda is some positive parameter, and this ST we introduce here to account for the turning on and off the laser field, because usually people assume that the laser is ideally turned on and off at some point, but here we take it into account, the energy cost and the disturbance that the laser field the turning on and off can cause. So ST you can choose different shapes for ST. Here in our work we choose it to be in this form, like sine to T. From 0 to T on means the moment is the laser is fully on. The shape of the laser would be a D form, and when it starts to be turned off, the shape will be again sine to T minus tau, and in between, so ST is 1. And we assume that T on and off the time duration will be like 0.005. Our time, since our times are of order of 100, and so sine 2 takes very small values. And we take the initial guess field to be of these forms and kappa is some constant, and we choose it based on the how convergent the evolution will be. This chi is chosen. Since we're going to minimize this functional, so J should in every iteration J should be less than the one in the previous iteration. As is proved in reference 4, in order for for the non-dissipative dynamics, equation 12 is satisfied when the update of the field is of this form. Okay, here there is a typo. This is dissipative. Sorry, this none shouldn't be there. The update should be of this form. Here, sigma is the backward state of the system for the backward evolution, and this is the state of the system for the forward evolution. And we use this shorthand also in here. Epsilon I means the field in the iteration I-1. After doing a lot of calculations, we get these equations of motions for the forward and backward equations in the dissipative case, given equation 15 and 16, where L rho is defined in equation 17 and L dagger in this form. Okay. Now we're going to apply this method to charging process of a quantum battery. We first apply it to a qubit model in which we assume that the battery is made of many cells and the cells are qubits. Okay, and the charger is also a qubit. So the Hamiltonian of the whole system of the charger plus the battery is written in equation in this form: HA plus HB. HA and B are the free Hamiltonian of the charger and the battery, and HAB the interaction between the charger and the battery, and this is the interaction between the field and the charger. So there could be many cells in the battery. So and also this is the interaction between the battery and the charger. G is the coupling strength. Okay, since again we assume that there is dissipation of energy into the environment through the charger, and the interaction is assumed to be weak, so the evolution will be given in equation 20, which was explained above. D is the dissipator defined in equation 7. We will compare our result with the case in which the field is not optimized. So the field is assumed to be an oscillatory field. And then we will see how the optimization can lead to better transfer of energy. Here HA and HB are the same, and HAB are the same as in equation 19 introduced above. As a figure of merit for our comparison, we introduce ergotropy. Ergotropy is a way of extracting energy in a unitary cyclic process. Assume that you have a system in state rho with internal energy of trace H rho. Okay, and then you apply a unitary to this system to some rho, to some other rho prime. So if then the difference between the energy will be like E rho minus E rho prime, and when E rho is the minimum energy, so from it you cannot extract any more energy in this cyclic process, then epsilon rho becomes maximum. Okay, and this maximum amount of work extraction is called ergotropy. So ergotropy is obtained by doing minimization over all unitaries that takes the system to the state with minimum energy, and it's called rho. This state is called rho p. P means passive. It means that you cannot extract any more energy in this way. Okay, another figure of merit that we use for our comparison is the energy used by the field, which is defined in equation 23. For the oscillatory field case, the energy cost by the field will be given in equation 24.
Borhan, you have 3 more minutes.
Okay, so here are the results for 1 qubit in the battery, and here is on the right 3 qubits in the battery. As you see, and the cyan lines are for the optimized case, and the black lines are for the oscillatory case. As you see in the single case, in the single qubit in the battery, both energy and ergotropy are higher than the energy and ergotropy for the oscillatory case, and also the optimized. You see, energy spent by the optimized field is clearly less. But as we increase the number of qubits in the battery, still for 3 qubits, there is more energy and ergotropy in the battery, but they approach each other. As you see, the shape of the pulse approach each other. Okay, here, and this case, this was for when the environment was in vacuum state. Here we increase the number of photons in the environment, and as you see, still this is the ergotropy versus number of photons in the environment. As you see, ergotropy in the optimized case is always higher, but as we increase n, they both go to 0. And energy cost by the field, as you see, first it decreases, because when we increase the number of photons in the environment helps a bit, and then since as we increase photon to the environment, it also noise increases. Then laser needs to spend more energy, and then it increases. And then since it cannot send the system to the desired state, it will stop feeding energy. In all cases, in all temperatures, the energy used by the oscillatory field is 31. Okay, I will go to oscillator-oscillator model, which is the main result of our paper. So here the Hamiltonian, we have 2 oscillators. Hamiltonian will be given in 25. HA and HP are given by 3 Hamiltonians of the oscillators, and this is the interaction. And the evolution also will be also dissipative, again, like in equation 7 with this dissipator. Okay, we'll go quickly. Since Hamiltonian is quadratic, then the state of the system, if it's Gaussian, it will stay Gaussian, and then a Gaussian state can be described fully by first and second moments.
Borhan, so I'm literally standing. You are running out of time, so this is more or less time for questions. But yeah.
Okay, can you see 30 seconds? Like yes.
Sure. Yeah.
Okay. Then we define these first and second moments. First, this vector of R. Okay, and then we define the first and second moments using this vector in 29 and the covariance matrix in 30. Then the equations of motion will be given in 34 and 35, which are corresponding, which correspond to the GKLS equations. We construct it, we encode all this information in this wave vector, and then we obtain these forward and backward equations. With this, again, this is the update, and these are the results for the oscillator. Again, we see that by optimizing, using the optimization, again, we increase the ergotropy and energy. This is for when there is 1 photon in the environment, and this is for the case when there is no photon in the environment. And then this one is for a longer time. Here we just increase time. Even when we increase time, we get even better ergotropy and energy because it gives more time to the field. Okay, here are the references, and thank you so much.
Thank you.